Hello, my name is Konstantinos Gambropoulos. I'm a PhD student from the University of Ioannina, and I will present you adaptive indexing in high-dimensional metric spaces, a joint work between the University of Ioannina in Greece and Aarhus University in Denmark. Constructing and maintaining an index for high-dimensional data can be quite expensive and may not pay off if the number of queries against the data is not large. Consider a setting where there is a need to query data that are frequently updated and past data become quickly obsolete. For example, satellite images depicting weather phenomena or other transient information. There is a need to quickly detect the phenomena before the next batch of images arrive. In these circumstances, it is more beneficial to construct an index adaptively while responding to query workload. Existing work on high-dimensional adaptive indexing uses hyperplane partitioning. That means that the inner subspaces are used to create distinct divisions between data objects in multi-dimensional spaces. However, partitioning the space into hyperrectangular units does not scale to high-dimensional spaces and does not apply to generic metric spaces. Besides, these methods do not cater to KNN queries, the most popular query type in high dimensions. Currently, the most effective non-adaptive indexing method for high-dimensional data is pivot-based indexing. These indexes select a few pivots, partition the space based on them, and use them to prune the search space guided by the triangle inequality. After talking about our motivation, let me guide you through our approach. We are building upon the idea of pivot-based indexing. Pivot-based indexes choose an arbitrary set of pivots, store pre-computed distances to these pivots, and use the triangle inequality to reduce the search space. However, we adjusted this idea, and instead of using an arbitrary set of pivots, we are using the queries as pivots. To make it adaptive, we follow the database cracking principles. Starting with an unorganized array of objects in memory, each new query reorganizes the data array and introduces cracks, and a tree structure is employed to keep track of the cracks. Again, we extended this idea. We are using a different tree structure to store the index information and use the triangle inequality to efficiently traverse the tree. I will give you an example shortly to help you understand our index. These two ideas, together with our extensions and adjustments, form the AV tree. Before I start with the example, let me give you some preliminaries. We examined similarity-based queries, namely range and k-nearest neighbor queries in a metric space. Data are stored as a sequence of feature vectors in a static array in memory. We aim to exploit previously evaluated queries to expedite the evaluation of subsequent queries. To achieve that, we use the triangle inequality to determine whether and how the range of a previous query overlaps with that of a current query. We have four cases. Queries can have no overlap, or they can partially overlap, or they can fully overlap each other. The AV tree is a binary search tree. Each node U contains two elements, low and high, that define the range of data array indices that node U indexes, and the query Q with radius epsilon that caused the crack if U is internal node. If U is a leaf node, then Q and E are null. Internal nodes have two pointers, left and right, to the left and right children respectively. Objects in the scope of the left side have distance less or equal than epsilon, meaning they are results of that query, while objects in the right side have distance more than epsilon, meaning they are not results. Let's go through an example to better understand the index. We start with an uncracked array of 8 2D objects, P1 to P8, and a root node V1 with low 0 and high 7. Then query Q1 with radius epsilon 1 comes. As there is no indexing information yet, we scan the whole data array to find the query results, and at the same time we crack the data array into two new pieces, one containing the results of query Q1 and the other containing the rest of the data. The query results are in the scope of the left side of V1, meaning the results are in position 0, 1, and 2 of the data array, and the data objects are P7, P2, and P5. Then query Q2 with a search radius epsilon 2 comes. As query Q2 overlaps the previous query, we have to visit both the left and the right subtree. Starting from the left, we have to examine the objects in the data array between position 0 and 2. As there are no data points in the overlapping region of queries Q1 and Q2, we get no results and an empty CRUG is created. But empty CRUGs do not provide any useful information to our index, so we avoid creating them. Then we go to the right subtree. We scan the piece indicated by the scope of a node, that is from position 3 to position 7, compute the distance to each point, and find the results while simultaneously introducing a CRUG to accommodate the query results. So what about KNN queries? Like range queries, KNN queries crack the data and progressively construct an AV tree. The difference is how we access the nodes. In this case, it is more beneficial to access them in a best-first manner. In addition, KNN queries introduce an interesting challenge as they do not offer a distance bound. We define such bound as the distance between the query object and its running kth nearest neighbor. Our KNN search algorithm uses two priority queues, a minimum priority queue that organizes unvisited nodes by least possible distance to the query in order to guide the search in a best-first manner, and a maximum priority queue that holds the running KNN data objects. Let me guide you through another example, this time for KNN queries. Consider this setting where we want to find the three nearest neighbors of a query point. Query Q1 is already answered and the array is cracked, and our tree has index information. Then a query Q2 comes. The algorithm starts by pushing the root node to the search priority queue. Because V1, the root node, is an inner node, we have to examine its children. We dequeue V1 and add its children to the search priority queue, ordered by their distance to the query in ascending order. Then we dequeue the top element of the search priority queue, that's V3. And V3 is a leaf node, so we have to examine all data objects in its scope. While result priority queue has less objects than K, we push the objects into it. So we push P1, P6, P4. Now the result priority queue has exactly K objects. So before pushing an object, we have to compare its distance to the running kth nearest neighbor, which is located at the top of the result priority queue, as it is a maximum priority queue. Here it is P1. P3 is closer to query 2 than P1, so P1 is removed and P3 is added. We do the same for P8, but because it's far away from Q2, we don't add it to the result priority queue. At the same time, we crack the data array using the distance to the kth nearest neighbor as bound. The algorithm continues until the search priority queue is empty. Now we examine node V2. But because the distance between the two query points is larger than that of the running kth nearest neighbor, we can omit the distance computations for the object in the scope of V2, as it is guaranteed that we will not find an object closer to Q2 than the running kth nearest neighbor. Then we introduce some enhancements to significantly improve the performance of the AV tree. First, we crack leaves using a sample-based mediocre pivot. When we crack a sub-array corresponding to a leaf node, we use a small sample of the already computed distances to compute the mediocre pivot. We confirmed experimentally that with as few as 3 samples, mediocre-based cracking is superior to the default strategy that cracks on query-bound epsilon or running kth nearest neighbor distance. Besides, mediocre-based cracking leads to a more balanced tree, since each crack yields 2 partitions of roughly the same size. We also noticed that our default algorithm is cracking leaves unconditionally. However, leaves that contain few objects are not worth cracking. In practice, they increase the tree height without offering a significant pruning advantage. To fix that, we stop cracking leaves if their size falls below a threshold. We call these leaves fixed. Last but not least, as distance computations consume most of the query evaluation time, we employ distance caching to reduce them. While cracking, we cache each object's distance to the current query. The next time we visit a node, we may use triangle inequality and the cache distance to check whether the object can be a query result and either prune it or add it to the result set, avoiding distance computations. In addition, cached distances are sorted to achieve an early termination of comparisons. To minimize the distance caching overhead, we only apply it on fixed leaves. To prove the effectiveness of our method, we compared it to some other methods. First, we compared it to linear scan, then simply pivot, which is a simply pivot-based index. In this method, the first pivot is chosen arbitrarily, and each subsequent pivot must have the maximum possible distance to the set of previous pivots. We experimentally chose the number of pivots to be 5. Then we compared it to adaptive KD3, which is the state-of-the-art for adaptive index of multidimensional objects, and MVP3, which is the state-of-the-art for indexing high-dimensional objects non-adaptively. For our experiments, we used the MNIST dataset, which is a dataset of 70,100 digits, then a synthetically generated cluster dataset with 5 clusters, and words, which is a database of 650,000 proper nouns, acronyms, and compound words. Query workloads are formed by randomly sampled objects from the data. The first experiment depicts the effect of dimensionality on the compared methods. The top row shows the per query time, while the bottom one the cumulative time for a query workload of 1,000 queries with 100 selectivity and any MNIST data of varying selectivity, varying dimensionality. Keep in mind that in the cumulative plots, we include the index building time for non-adaptive indexes. AV3 exhibits the ideal behavior of an adaptive index. Its per query cost drops gradually until it reaches that of a pre-built index as MVP3. Adaptive KD3 performs competitively in low dimensions where hyperplane-based partitioning works satisfactorily. As data dimensionality grows and until the adaptive KD3 reaches its threshold, it creates up to 2D levels per crack. That leads to a very tall tree that is expensive to traverse. Here is the same experiment repeated for KNN queries. We excluded the AKD as it does not support KNN queries. And as you can see, the results are consistent to those for H queries. We also experimented with workloads of varying selectivity. The relative performance of all the compared methods is unaffected by the workload selectivity. Lastly, we examined the effect of data size in the performance of these methods. As you can see, all methods are equally robust to data scale. To conclude, I introduced to you the AV3, an adaptive index for high-dimensional data in metric spaces. The AV3 partitions the space around query centers into units defined by hyperspheres using mediocre distance bounds that naturally adapt to the data distribution. Our experiments showed that it adapts to the query workload to progressively build a complete high-quality index. Thank you for your time.